Hello everyone, welcome or welcome back to the Next Level FAANG YouTube channel. So today we'll be solving another very interesting problem. It is called the word squares problem. So this particular problem is a Leetcode premium problem, by the way. So do hit that subscribe button for more such premium content coming your way. So let's get right into the problem now. So given an array of unique string words, we have to return all the word squares we can build from the words. The same word from words can be reused multiple times. So you can return the answer in any order. So a sequence of strings forms a valid word square if the kth row and column read the same string, where k is between 0 and max of num rows and num columns. So for example, the word sequence ball, area, lead, and lady, it forms a word square because each word reads the same both horizontally and vertically. Let's look at this problem in more detail. So looking at the goal we have, so we want to form word squares, which means arrangements where kth row equals kth column. Now let's see what a word square actually means. So here, as we can see, we have a word ball written over here. This is, let's say, our word array we have input in the question. So this is the zeroth row. This is the zeroth column. If we see that the zeroth row has the word ball, and when we read the zeroth column, it also comes out to be a ball. Similarly, the zeroth column is area. So the first column is area, and the first row is also called area. Similarly, the second column is lead, and the second row is also lead. And last but not the least, we have the third column as lady and the third row as lady as well. This is what a word square comes out to be. So now when you look at it, so if I talk about an approach, so the first step here says build a trie. So now why we are using trie as a data structure and not using any brute force approach? In this case, especially the brute force approach is actually very, time consuming because if we look here, so what this problem is actually doing. So let's say here we have a word ball. We start with the word ball. So, what do you think? What the next step should be? As in, when we get to the next word here, let's say the next word has to start with A because we have to make the column also look like ball. So, the next word has to start from A. So, we need to actually look for every word who has the prefix A. Moving on, if we have spotted the word, let's say it's area. So, moving on, the next word has to start with A and not A exactly. So it has to start with L and E so that in a way we can form the word square accordingly. So if it starts with, let's say we have spotted LEAD. So if we look at this, we have VAL ready already. Then we have ARE ready as well. So it's building to what we want it to be. Like it's building to be a word square. As we can see here, as if I this word array, it let's say it increases, it is not limited to 4 words, right? It can go up to let's say n entries. So if it goes up to n entries, then a brute force solution is basically, you know, a, like extracting the prefix and then looking for a word which matches that prefix. So we will have to make n comparisons of, let's say the length of the string is L, and then we have to match the prefix with n words in total. So this process itself for every prefix match can go up to, let's say, big O of n into L time complexity, and this is for every prefix match. So if we are doing multiple prefix matches, then it goes like up to it will be an insane time complexity to look at. So if you look at the approach now, so building a trie. So trie is basically, if you're aware, it's like a data structure, which basically if we build once, it is also known as a prefix tree. So it has like a root node, and then we have children, which we build according to the words we are having. Let's say a sequence of strings we have, and we are trying to convert it into a prefix tree. So it basically starts with a root node where we keep on adding children and then adding more child nodes as soon as we have catch a similar pattern. So we'll talk about it later as well. So basically building a trie here, it helps us like getting a structure first. So building a single trie structure will take only big of n cross L, the time complexity, n into L time complexity. And once the trie is obtained, then we just will be able to easily look at matching prefixes in big O of L time complexity, where L being the length of the string, or the number of characters we are looking at, number of characters in the prefix. So now building a trie, what we'll do, we'll insert all words into a trie, and at each node, we'll store a list of word indices. That is basically that I share the prefix up to that particular node. So backtracking in this particular case is happening as well because we need to backtrack every time this a particular solution, a particular set of solution. Let's say we have ball, we have area, and we have two other words. We have lead, and we also have let's say we have leap as well. So if lead is not working and is not bringing out any solution, so we'll have to backtrack and take leap, try leap, so that if we can come up with a word square. So backtracking DFS is also happening. So for each word in the list, we treat it as the first word in the square. We try to build the square row by row using DFS. So the first word definitely will enter the square so that we start somewhere. And then we try to build square row by using the DFS. The DFS search, basically searching the prefixes. And at each level, we'll form the prefix of the next word by taking the kth character of each word so far. K is the current depth. We'll also keep a depth, like just to keep a track, because if we look here, the length of the string matches the number of words in a particular word square. So we'll also keep a check using a variable depth. So and we'll use a try to find all words because that is the most efficient way to for pattern matching, for prefix matching to be specific. So let's start with that particular prefix and then we'll recursively try each candidate. So once it is done, the prefix matching happens. The prefix lookup allows us to efficiently find matching words instead of scanning the entire list each time. This is happening using the trie data structure we are using. And the base case is basically we break as and when the current square size will be equal to the word length. And we simply add it to the result because we are looking for multiple results here. So let's take an example test case, the same test case we were talking about, area, lead, wall, lady, and ball. So step one is basically constructing a tribe. So when we see that there is a root node, the root node has multiple children here, four children to be specific. So we have the first word area. Here, no other word starts with A, no other word starts with AR, no other word starts with ARE. So nothing, there's no other children coming out of, let's say, AR. We don't have another path to traverse here. We only have one and it gives us area. Similarly, we have ball, but for lead, because we have two words starting with L. So here we can see L breaks up into two parts. We have one for lead and we also have one for lady. So this is how a trie is basically constructed. I have just given a basic picture right here. So we can see and visualize the trie just like it is done here. And also we are keeping a track of the word indices. So as I said, the word indices is basically storing that share the prefix up to that particular node. So it is basically storing a list of word indices that share the prefix up to that particular node. So let's get to step two. Once we have the trie ready, so the every word, so we have to try every word as the first row. So we'll start DFS from each word in the list. So the first loop word in this case is, let's say, ball. So we have ball, and in the start we'll just add ball because we need to start somewhere, right? So we add ball to our result, and we build prefix for second row. Here we are at depth 1. Depth 0 has been accomplished by adding ball to the square. So we are at depth 1 now. So we want second row. So we'll form the prefix. We know that we also want that the kth column, like the 0th column should also be ball. So the first word has to be A. So prefix has to be A because ball first index is A. So we search the trie for prefix A and it returns area because we only have one word starting with A. So it returns area and we add area to the square. Next, for the third row, similarly, the depth is now 2. Now we want the third row to form the prefix. Now we are aware that LE is something we are looking at. So that the first letter here is L and then we have ARE for the area. So from ball area, we extracted L and E from ball second and the area second index. And then we search trie with LE, which returns us lead. So we add lead in the square. Now for the fourth row, similarly, we have prefix LAD. We already have these three added to the square. And then we search trie with lad and it returns lady. So we add it here and now we have valid word square where we store it simply. So now we backtrack. Now we'll pop lady. We'll drop lady from the square and try other candidates for lad. There are none other candidates starting with lad. So we pop lead even. Now we try other options. Now there are none. So we backtrack all the way up. So what is the next loop word? Now we start with ball, because for ball, only this is the one square that worked out. But we also had wall in our input. So let's start with wall this time. So it repeats the same step, and then we find out that there's another word square, which has wall area, lead, and lady. So this way, another valid square is found. So the final result now has two sequences. First is the wall area, lead, lady, and then we also have wall area, lead, lady. So this is basically the approach we are looking at currently. And now also let's look at the code. So this is the code to the discussed approach. So we first have the trie data structure implementation. So here we have the class trie, which we are defining to support the prefix-based lookup operations as discussed. So we have the we map each character to its corresponding trie node. So this is keeping track of all the children. Then we have the word indices where we are storing the indices of words in the dictionary that pass through this particular node, which basically share the same prefix. So we are keeping a track of that as well. So next we have the insert function where we are inserting each and every word character by character in the prefix tree, which is the trie. So for every new for every new character which is not in the current character path, we create a new node in the trie as well, as I've shown in the illustration as well. So we are checking if we don't have it, then we are actually having a new node in the trie. So and then if we have it, then we move to the child node corresponding to the current character, and we append the words index to the list of the indices of the prefix node. So next we have the search operation where basically we are searching for all word indices that match a given prefix. So then we have we are again going character by character. So if a character in the prefix doesn't exist in the trie, so we return an empty result. So we can see here as well a similar thing we have done. So if there's no match, we return an empty list. Then we move to the next node in the prefix path, and then we return all the word indices that have a specified prefix. So this is basically the implementation of the trie data structure. Now we're coming to the core word squares builder. So here we can see that we are having the trie for efficient lookups. Then we have a dictionary that stores the input list of words. Then we also have the final list of the valid word. So there we have this function called build square, which is taking the current square, so that this is basically a recursive backtracking function, which is basically to construct the word square. So the base case is again if the square is complete, that is when the size is equal to the word length of the word we are currently dealing with. So we push back the result in the current square and we return. So moving on to the next, then we build the required prefix for the next word in the square. So we keep a string prefix, and then we also calculate the depth, which is basically the current level in the square. Level as in being the because if the level reaches the, let's say, the number of one less than the number of letters or the character length we have for the word, then we have to stop it and check if we can add it to the result if it is a valid square. So then we collect the character from each word at the current depth so that we can form the prefix as we were extracting the prefix and then comparing so that we can find a prefix matching in the trie that we have done here. So we use the trie to fetch all words indices that match this prefix. So now we attempt to extend the current square with each matching candidate. So as we can see, we are adding the next word. We're pushing back the next word, and then we are building square with the current square. We are recursively filling the next row, and then also for the current square, we are popping back the element as we were popping back the last element found if it is a complete square even, so that we can look for more ways or more word squares in this problem. So we backtrack to try another candidate if we can achieve another square or if the current square is not valid. So moving on, we have this word squares function also, which is basically the entry point, builds the trie and also initializes the recursive search we have defined earlier. So then we insert each word into the trie with its index for prefix-based searching. As we can see, we are inserting each word with its prefix for the prefix-based searching. Then we have the current square defined here. So now we attempt to form a word square starting with each word. So we have the current square, we're pushing back the first word we are starting with so that we are starting with something. Then only we'll be able to build the square. So now we are using the build square function we defined. So it recursively build the full square, and then we backtrack for the next starting word. And finally, when we have obtained all the possible word squares, we return the result, which basically returns all successfully constructed word squares. So this is basically the implementation of the entire problem. Now let's look at the time complexity and the space complexity. So I have a small analysis here so that we can follow along together. So we have n, the number of words of the list, and we have L, which is basically we're calling the length of each word. In this case, all the words have the similar length. Then K, which is the average number of matching words for this particular prefix. So step one, we are building the trie. So it has to be n cross L and n into L, big O of n into L time complexity as discussed earlier, because each word is of length L and we have n, we have to insert n words. So for each character, we store the index. So the every operation it is big O of L. So it comes out to be the entire construction takes big O of n into L time complexity. Then we have the backtracking. So the depth of the recursion is L. Firstly, we are calling the bill square n times because we have n words. It's mentioned that we have n calls. So we are calling this n time. Then we have the depth of the recursion as L. Constructing a prefix comes out to be big O of L. Then searching that prefix in the trie is also big O of L because where L is the length of the word. And let's say on average, k words are matching per prefix, as I said earlier as well. So number of recursive paths has to be k to the power L, and the time per path is big O of L. So the final total time the entire program is taking is big O of n into L, which is earlier for the operations. Then we have number of recursive paths also multiplied here, which is k to the power L. So the final complexity comes out to be big O of n into k to the power L into L. Then next, the space complexity analysis. First, let's analyze the trie storage. So each node can have up to 26 children. It's very well understood. So each node stores a list of word indices, which is up to n again. Then we have the trie depth is L. So it has to be n into L nodes in total with each with children plus indices. The space taken is also big O of n into L. Then we have the recursion stack, where at most L levels be, and each level holds a string and prefix. So it's again big O of L. So total has to be big O of L square, combining these both. And then the output storage, if at worst n choices for L, each of L. At worst n choices for each of L positions. So we have n to the power L square, and for each square has L words of length. So we have L square space per square. So it comes out to be big O of n to the power L into L square. So the total space complexity analysis, if we look at, so combining this, and this here. So we have the final one, which is the dominant factor. So we take big O of n to the power L into L square as the final time complexity. So the result vector is basically, which is taking most of the time. So it is dominated factor. So we are make the final one has to be big O of n to the power L into L square. So this was the entire answer to the problem word squares. I hope you enjoyed the solution and you were able to follow along with me. It's a bit tricky problem, but as we go ahead, we understand it better. So trie it, and data structure implementation is also something we learned through this problem. So do hit that like button and also subscribe to the channel for more such premium content coming your way. Thank you.